Build that wall. Build that wall.
Build that wall was a campaign promise simple enough to chant and vague enough to sound inevitable. But the moment crews had to turn that slogan into steel and concrete, the idea collided with physics, terrain, and procurement. What rose in the field was rarely a solid monolith. It was a repeating industrial system. Tall, see-through steel bollards, fabricated into lift-ready panels, set with cranes, and locked into fresh concrete, one segment at a time. And it never advanced as a single, continuous line from ocean to gulf. It moved in targeted stretches, each with its own access fights, design tweaks, and supply chain clock. If it looks simple from far away, why does a single mile demand precision alignment and non-stop concrete work? The answer isn't what most people think. It isn't the steel, it isn't the concrete, it's the hidden ecosystem around them. An operating cost that can outgrow the materials combined, and the reason schedules slip even when crews are ready to build. The $15 billion number is best understood as the cost of that ecosystem, not just a stack of steel. The visible barrier is only the spine. Contractors also build and rebuild access roads, crane pads, staging yards, drainage structures, lighting, gates, and the turnouts that let Border Patrol reach the line in minutes instead of hours. Each item pulls its own permitting, deliveries, inspections, and repair cycle. That is why cost per mile swings so widely. It depends on distance to pavement, power, and a concrete supply that can reliably reach the site. Procurement adds another layer. Instead of one mega contract, the government awards multiple packages across sectors, often with different prime contractors and schedules. And that's where the timeline starts to fracture. The wall can be ready in one sense, crews mobilized, equipment staged, while the job is still frozen by a single missing dependency. Which one breaks first depends on the segment, but the pattern is consistent. Steel lead times, rebar availability, coating windows, trucking capacity, and concrete delivery reliability all have to line up at the same time. Even crane time becomes a resource you schedule like fuel. If a lift plan slips a day, the sequence behind it stacks up. Panels arriving early need secure laydown space. Panels arriving late idle welders and inspectors. Timelines also get distorted by what miles built actually means. When you hear a mileage number, it sounds like the wall advanced into empty space. Often, it didn't. Much of the work is replacement or upgrade. Older vehicle barriers or low fencing gets removed and rebuilt to a newer standard. It still consumes survey work, demolition, disposal, and new foundations, but it does not always create newly walled border in the way people assume. Terrain is the multiplier that turns a standard detail into a different job. In open desert flats, the workflow can look factory-like. Grade access, cut trench, set rebar, pour, and fly panels into place. Move that same system into mountains and the wall becomes logistics first. Switchbacks for trucks, pads for cranes, and stabilized slopes so equipment is not working on unsafe tilt. Along floodplains and washes, the schedule gets held hostage by weather windows and drainage details, because a section that blocks flow can wash out and strip foundation soil with it. Throughput is limited by the slowest input. How fast trench can be opened, how reliably concrete can be delivered, how many welds can be inspected and accepted, and how long temporary roads stay passable after storms. So how do you set 30-foot steel panels on a remote ridgeline without turning the site into a permanent industrial highway? There's a specific technique that lets crews install entire sections in a single day instead of weeks. It's counterintuitive, and it changes what fast even means on a remote, high-friction job site. The answer starts with how steel arrives, how it's staged, and how it's assembled into panels that a crane can place in minutes instead of hours. Most modern border barrier segments use a steel bollard system because it solves two competing requirements at once: It blocks vehicles and slows climbing, while still giving agents line of sight through the fence. The typical height range runs from about 18 feet in some areas up to roughly 30 feet in others, and that extra height is structural. Taller members see higher bending loads from wind, so post geometry, spacing, top anti-climb detail, and the foundation have to work together. But the uncomfortable truth is that steel and concrete is not the same as unbreakable. Border authorities have confirmed that commercial reciprocating saws, tools you can buy for around $100, can cut through bollards in minutes. More than 3,000 bollards have already been breached using that method. That does not make the wall pointless. It clarifies its real job, not absolute prevention, but delay, channeling, and control, buying time for detection and response. The basic element looks simple: a vertical, hollow steel tube, usually rectangular, repeated with a narrow gap between members. But specs shift with corrosion exposure, especially near river environments where periodic wetting and sediment abrasion can punish coatings. That pushes protective paint systems, galvanizing where appropriate, and steels selected to reduce long-term maintenance in remote terrain. The process begins in fabrication yards, not on the border. Bollards are cut to length, drilled for connections, and welded to headers or stiffeners that let multiple members act as one liftable unit. What matters here is tolerance. A small twist or pull from welding does not stay local. It becomes an alignment fight later, panel after panel. This is why shop-level quality control directly determines how fast crews can install in the field. Once panels are fabricated, the border job site starts to look like a moving warehouse. Flatbeds deliver stacks of steel to laydown yards, where forklifts and cranes stage them in the order they'll be set. Sequencing is the discipline. If the install crew can lock in a certain number of panels per day, deliveries have to match that tempo. Too early, and you add extra handling that can nick coatings. Too late, and operators and inspectors wait while equipment idles. Panelization is the key speed trick. Instead of lifting one bollard at a time, crews assemble several into a single panel, so each crane pick installs a larger bite of wall. Fewer picks mean less rigging and fewer chances to misplace a post by an inch and spend the next hour correcting it. It also improves consistency because the panel's internal spacing is fixed in the shop, leaving the field crew to focus on setting and aligning whole units to the control line. Alignment is where the simple fence becomes precision work. Crews stretch tension lines, shoot grades with laser levels, and brace panels so each one stands plumb and meets the design spacing to the next. A small lean becomes cumulative. If a panel tilts even slightly, the top spacing changes, and the next panel won't meet cleanly, forcing rework in a trench that may already be partly filled with concrete. But there's a weakness that has nothing to do with plumb lines. Border officials have been shocked by how quickly a finished section can be opened up with something simple and widely available. And once it happens, all that careful spacing and alignment becomes irrelevant. And none of those upgrades matter if the base can't hold. Steel can only stand at speed when the foundation behaves like a continuous footing, ready to accept panel after panel without settling or drift. That's where the next bottleneck begins. Excavation, rebar continuity, and a concrete operation that has to run like a pipeline in the middle of nowhere. The foundation work starts with a trench that sounds straightforward on paper, roughly 24 to 32 inches wide and about 6 to 10 feet deep. In soft desert soils, excavators can cut that profile quickly, then a trencher cleans the walls and bottom so the line stays consistent. In fractured rock, the same trench turns into a demolition job. Rock breakers advance in short bites, and overbreak has to be controlled so concrete does not disappear into voids that waste volume and weaken support. Once the trench meets grade, crews drop in a continuous rebar cage. This is where the wall behaves less like a fence and more like a beam. Reinforcement needs to run uninterrupted so bending loads from wind and impacts do not concentrate at one joint. Dowels, embedded plates, and anchor assemblies tie panel bases into the cage, so when the concrete hardens, wall and footing act as one structural unit. Concrete placement is a logistics problem disguised as a pour. Some sites can support mixer trucks backing to the trench. Remote sites rely on pump lines, with deliveries timed to avoid cold joints. Consolidation matters because air pockets around embedments become future crack starters. So crews vibrate the concrete along posts and hardware, then manage curing and heat that can drive rapid set and shrinkage. In selected areas, anti-undermining measures show up as widened pads or thicker foundation geometry extending outward from the wall. Extra concrete changes the digging problem and improves resistance to erosion, but it also increases pour volume and rebar tonnage, so it is used where the risk profile justifies the schedule hit. Flood behavior is the failure mode that catches attention after crews leave. In arroyos and wash crossings, stormwater can undercut the foundation and strip backfill. Near riverbanks and floodplains, the wall can act like an unintended dam if drainage openings or gates are not sized correctly or operated on time. That pushes engineers to add drainage structures, and in some locations, gates designed to be opened during storms. Each one another maintenance item in remote terrain. Then comes the most visible add-on, Concertina wire. It is a coiled, galvanized steel obstacle with flat, blade-style barbs, packaged in tight rolls and expanded on-site like a spring. It is typically used selectively, not end-to-end across the border, because material and labor scale quickly and installation is hazardous. The method is simple but unforgiving. Crews move coils with forklifts or tractors, stage them along the top line, then stretch them in sequence and tie them into brackets. Uneven tension creates sags that are easier to manipulate. Overtension can snap back during fastening. It adds deterrence, but it also adds inspection and replacement work after storms, impacts, and cutting attempts. And that but is unavoidable. A physical barrier can slow and channel movement, but breaches, washouts, and wear keep the system in active engineering mode long after ribbon cuttings. That is not a side effect. It is the operating model. When you build across floodplains, deserts, and rock cuts, the engineering shifts from build once to keep it working, with repairability and access treated as core requirements. Here's the reality. As of 2025, less than 40% of the US-Mexico border has any physical barrier. Hundreds of miles remain open by design, by terrain, or by politics. And the bill keeps climbing because this is not a build-it-once structure. It is a life cycle project. Breaches, washouts, corrosion, and shifting ground do not end the story after installation. They define the operating schedule. In practice, the wall functions like a permanent construction site and a living laboratory for what happens when steel, concrete, and drainage are forced to coexist with deserts, mountains, and floodplains. So the question isn't just whether it gets finished, it's whether constant repair and adaptation is sustainable at this scale. Share your take in the comments, and in the next video, we'll break down the surveillance technology filling the gaps the wall can't.